Our last unit for modern physics is going to look at the subatomic particles. So we're looking subatomic level and we're going to look at what all matter is comprised of. So all matter is comprised of leptons and quarks. Right? So all matter can either be classified as being comprised of leptons or being comprised of quarks. And in your reference table, there is a chart that has both leptons and quarks on it. There's actually two charts that we're going to be referencing for our subatomic portion of modern physics. So we'll talk more about those. The other thing that you need to know with subatomic particles is the force carrier particles hold all matter together. There are four fundamental forces in nature. The strong force, which we talked about in a previous video. Strong force is going to hold the nucleus together. You have the weak force. You have the electromagnetic force, and then you have gravity. Right now, these forces, these four fundamental forces, have been placed in order of strength from strongest to weakest. So the strong force is the strongest force in nature. The weak force, even though it's called the weak force, is actually quite strong. Right? That's the next strongest. Electromagnetic, and then gravity is actually the weakest force out of those four fundamental forces. Right? That's a great thing to know. So I definitely write that down somewhere and make note that those are in order of strength from strongest to weakest. So let's look at what quarks and leptons are. Quarks and leptons are subatomic particles. They are fundamental particles that are incapable of being subdivided into anything smaller. So a lepton is a lepton, right? We'll talk about 6 different types of leptons, and those leptons are composed of nothing smaller. Same thing with quarks. There are 6 different flavors of quarks that we'll talk about, and a quark is a quark. There's nothing smaller that makes up a quark. Right? The reason we're talking about this is because protons and neutrons, things that you've learned about before that are in the nucleus of an atom, they are made up of smaller subatomic particles, which are actually quarks. Right? So quarks are as small as they come here. Lepton is a lepton. Great things to know. Letter B here says the nucleus is a conglomeration of quarks which manifest themselves as protons and neutrons, right? And so that's something I just said. Proton is made up of a combination of quarks that gives the proton a charge of +1. A neutron is made up of a combination of quarks that give the neutron a charge of 0. The other thing to take note of with leptons and quarks in every elementary particle is the fact that they have a corresponding antiparticle, which makes up antimatter. So if you're really into this modern physics and things that scientists are actually really studying today, right, in the modern world, you may have heard about antimatter and antiparticles. So we'll touch on that just a little bit as we go further in here. Okay? So before we get into matter versus antimatter, what I want to do is show you the chart on your reference table. So here is your reference table, right? This is page 3. And right now I want to look at the right-hand side. And you'll see on the right-hand side you have quarks. And each one of these boxes is a different quark. And so there are 6 of them, right? You'll see here that you have the name of it. So there's 6 of them. They're named strange things, right? There's an up quark, a charm quark, a top quark, down, strange, and a bottom. Right? The next thing under the name you see is the symbol. So the symbol for that quark is just the first letter of its name. Right? So up is U. And then you have the charge. So you'll notice that quarks have a charge that's a fraction of an elementary particle. So we talked about earlier this year how the charge on an object cannot be a fraction of the charge of an electron. Okay? Here's the exception. Quarks have a charge that's a fraction of 1 elementary charge. The thing, though, with quarks is that they must be a conglomeration. You have to combine a certain number of them to create a whole number charge. Right? They cannot just exist on their own. They have a very short lifespan. They're very unstable if they are by themselves. Okay. Underneath, you have your 6 leptons, right? So you have the name, you have the symbol, and then you have the charge. So you'll notice right away the first lepton that's here is the electron. Okay, an electron is a lepton. So an electron is not made up of anything smaller. Right? The other leptons you have are the muon and the tau. Notice they all have a charge of -1 elementary particles, just like the electron. And then you also have electron neutrino, a muon neutrino, and a tau neutrino. So all 3 of our leptons have a neutrino counterpart, right? And the neutrino is neutral. Okay, now, so for all 12 of these particles, all 6 of the quarks, all 6 of the leptons, there is an antiparticle that corresponds. Right? So let's go back to the presentation here and talk about antimatter as well. So matter versus antimatter. For every particle, there's an antiparticle. Right? Things to know about antiparticles. They have the same mass as the particle itself. Antiparticles have the same magnitude of charge, but it's the opposite sign. So for example, an electron has an antiparticle, an anti-electron. Same mass as the electron, but it has a +1 charge. Right? And then the other thing to take note of is that antiparticles have the opposite spin. We're not going to get too much into the spin, but if you take physics in college and you move on, you will talk more about the spin. Antiparticles for antimatter spin in the opposite direction. Right? So here's an example. We're going to look at an up quark, right? So the particle that we're just looking at here is an up quark. The symbol for it is a U, right? We got that from your reference table. The mass is not something you need to know, but the mass of an up quark is 7.11 times 10 to the -30 kilograms. And the charge on an up quark from your reference table is +2/3 of an elementary particle, elementary charge. Okay? The antiparticle associated with an up quark is an anti-up quark. The symbol for it is a U. Notice, however, that there's this horizontal line over it. That is important, right? So anytime you have an antiparticle, you'll have that horizontal line above it to indicate to you that it's an antiparticle. Okay? So you need to know that that line represents that, and you need to know what it means. So for instance, the mass will be the same. However, the charge is the opposite sign. So you'll notice the charge on an anti-up quark is -2/3. Let's talk about leptons. So in the reference table, there are those 6 leptons. Okay? They are elementary particles. They really don't have any measurable size or structure. And there are 6 known leptons, right? So the electron, the muon, and the tau. And then each of those has a neutrino counterpart. So you have the electron neutrino, the muon neutrino, and the tau neutrino. Neutrinos do not have an electric charge, so they are electrically neutral. Okay? And again, all 6 of these has an antiparticle. So you have the anti-electron, the anti-muon, the anti-tau. You also will have the anti-electron neutrino, the anti-muon neutrino, and the anti-tau neutrino. Okay. So if you look at these things that I mentioned when we were looking at the reference table, the electron, the muon, and the tau all have a charge of -1 elementary particles. Okay. The electron is found in everyday matter. You know that, right? The electron is found in all atoms. The muon and the tau have a lot more mass than the electron, and they are not part of everyday matter because they have very short lifetimes, right? So they will not stick around in their state for very long. So they're not in everyday matter because they do have very short lifetimes. Neutrinos. So every lepton has a neutrino counterpart, right? So neutrinos are 3 of the 6 leptons. Again, they have no charge. They are very stable, and they really never interact with any matter on Earth. Quarks. So again, there are 6 quarks. We looked at the reference table. These are the building blocks of protons, neutrons, and then other nuclear particles. But the protons and the neutrons are the ones you really need to know. Okay. There are 6, we call them flavors. Sometimes you'll hear the word varieties of quarks. And they have to combine together so that they create a charge that's essentially a whole number. So you have to create a charge of plus or minus 1, plus or minus 2, plus or minus 3, or 0. Right? And so here are your 6 quarks, up, down, charm, strange, top, bottom, and their corresponding charges. Okay? And so we can combine these to create a proton and a neutron. Now you know that a proton has an overall charge of plus 1. So you could look at these and figure out how to combine a few of these particles to create plus 1. But a proton is a very specific combination. A proton are 2 ups and a down. So a proton consists of 3 quarks, an up, an up, and a down. So if you look at the charge of an up, you have plus 2/3. We're going to add another plus 2/3. And then a down is a negative 1/3. So you have 2/3 plus 2/3 minus 1/3, which gives you, essentially, 3/3. So you get 1. A neutron is also a very particular combination. A neutron is an up and 2 downs. So again, if you look at their charges, add them together, you do get a charge of 0. Right, now, there are other combinations that will give you similar charges, but when you combine different quarks to create other particles, they're given other names. Right? So very specifically, an up and up and a down is known as a proton, and an up, a down, and a down is known as a neutron. But you can combine them in any other way. If we were doing one of the lessons together in the classroom, there's kind of a game that we would play where you see how many particles you can come up with by combining quarks to create whole number charges. So the other thing we have to talk about are hadrons. Okay, hadrons are another part of this chart that we are going to look at. They consist of particles that interact through the strong force. Right? Now, hadrons are set apart from leptons because they're composed of other smaller particles. Right? They're separated into 2 categories known as baryons and mesons, and they are distinguished by their internal structure, so we will look at that. Most of the mass that we observe in a hadron comes from its kinetic and potential energy. Just a fun little fact. Right? But what I want to do is look more at how we distinguish between baryons and mesons. Okay? So before we actually do this, let's go back to your reference table. So on that same page, you also have this classification of matter. Right? So you have matter, all matter up at the top. And all matter can be broken down into either a lepton or a hadron. And this is what we're talking about right now, hadrons. Okay? But before we get into that, let's look at leptons. So if it's not a hadron, that matter is classified as a lepton. And if you have your reference table in front of you, what I would do is draw a line from leptons down to your 6 leptons. Right? So all matter can be classified as either a hadron or a lepton, and if it's a lepton, it's one of these 6. So the electron would be on this side of this chart. It would be right here. An electron is a lepton. Okay. Hadrons can be broken down themselves into baryons or mesons, and so we're going to talk about these, right? But this is distinguished by the internal structure, what they're made of. So a baryon is made up of 3 quarks. Not 4 quarks, not 2, 3 quarks. Right? It's classified as a baryon. A meson, on the other hand, is made up of 1 quark and 1 antiquark. So 2 particles, one of them is a quark and one of them is an antiquark. And they don't have to be, it doesn't have to be the antiquark of the original quark. Right? And so you'll see that as well. So let's go back to our notes, but just know that this is here. Okay? And you may want to add a few things to this chart if you have your reference table handy. So a baryon, right, is composed of 3 quarks, which you can read from your reference table. All but 2 baryons are very unstable. right? So when you combine quarks to create a particle, they are pretty unstable. So their lifespan is very short. So all baryons are pretty unstable except for two of them. And those two are the proton and the neutron. So proton is very stable, neutron is very stable. Okay? So in your reference table, next to that baryon section, I would add, make a note to yourself, a proton and a neutron are examples of this. Right? A proton is an up and up and a down, so it's composed of three quarks. A neutron is a down, or excuse me, an up, a down, and a down. So again, composed of three quarks. All right, mesons are composed of a quark and an antiquark. They're very unstable, right? So they have very short lifetimes. They're not part of everyday matter, and they decay into electrons, right? So they become a lepton, positrons, neutrinos, and photons, particles of light. Right? And so here is that chart. So again, you have matter, and it can be broken down as either classified as a lepton, like an electron. So again, I would draw a line from that box on your reference table over to your 6 leptons. And then if it's not a lepton, it can be classified as a hadron. Hadrons can be broken down into two subcategories. A baryon, like a proton and a neutron, that's composed of 3 quarks, or a meson, that's composed of a quark and an antiquark. Right, now the thing to realize here is you still have to, when you combine quarks, they still have to be a whole number. So it has to be +1 or -1 or 0. Same thing with a quark and an antiquark. You have to combine them. Here you're only combining two particles though. But when you combine them, when you look at their charge, it has to be a whole number. Okay. So again, here's our example. A proton is a baryon, and a meson could have a combination of a strange and an anti-down, or an up and an anti-down. Right. So again, an antiquark has that line over it, right? So for instance, an anti-strange has the opposite charge of a strange. Okay? And that is your subatomic particles and your classification of matter. So you can get all of that right from your reference table, right? So a lot of this final part of modern physics is really just understanding how to read the reference table, right? And to read these two charts.